In this video, we're going to introduce an important group called the alternating group, and for that we need to define the even and oddness of permutations. So a permutation sigma in the symmetric group on n letters is said to be even if it can be written as a product of an even number of transpositions, and similarly it's said to be odd if it can be written as a product of an odd number of transpositions. So remember that transpositions are cycles of length 2. They just transpose or switch two elements. And we've seen that any cycle of length r, there's a trick to write it as a product of transpositions. It turns out to be can be written as a product of r minus 1 transpositions. Namely, you use this trick here. Here's a little bit easier way to see this. In a particular example of r equals 5, you've got a 5 cycle, and this is a product of these transpositions. Namely, you take A1 and then work backwards forming these transpositions, and it's not obvious, but these two sides of the equations are equal to each other. Now, one thing that's maybe not so clear from this definition is, can a permutation be both even and odd? In other words, can you write it as an even number of transpositions, and can you write the same permutation as a product of an odd number of transpositions? And the answer is no, that's not possible. I don't want to go into the proof right now. Probably the easiest proof is using permutation matrices and their determinants. To apply this cycle, let me do a simple example. So consider the permutation 5, 2, 1 in S5, the symmetric group on 5 letters. And using that trick, this permutation, it can be written as a product of these two transpositions. You start with the initial number here, which is 5, and then work backwards forming these transpositions. And so we've written this as a product of two transpositions. And because 2 is even, we then say or conclude that the cycle 5, 2, 1 is an even permutation. Now, we can also write this cycle, obviously, as a product of 4 transpositions. Simply tack on some random transposition twice. So I've tacked on 3, 4, 3, 4 for no particular reason except to show that the way to write a cycle as a product of transpositions is not unique. This is not the only way. There's other ways, but this is just one particular way. And then here we've written the cycle as a product of 4 transpositions, and 4 is an even number, so that's consistent. We won't be able to write 5, 2, 1 as a product of an odd number of transpositions. So we see that a cycle of odd length is actually an even permutation. So unfortunately, you have to kind of switch the even and odd. And similarly, a cycle of even length is an odd permutation. Because, here's a cycle of length 3, and we've written as a product of 2 transpositions, and so on. So it's okay. So then the alternating group, this is the reason why we're introducing these even and odd permutations, is denoted A sub n. For every n, there's an alternating group. And this is the subgroup of S sub n, the symmetric group on n letters, consisting of even permutations. And every permutation, again, is either even or odd, and so the alternating group is those that are even. And it's a subgroup, so it has to contain the identity element. And why is the identity element an even permutation? Well, we can write the identity element as, for example, 1, 2 times 1, 2, and that's a product of 2 transpositions. Now, the set of odd permutations is not a subgroup because it doesn't contain the identity element. Okay, now another completely different fact is that the order of an R cycle is R. Remember, the order means what's the smallest power you have to raise the element to get the identity. And so if the permutation is A1 to A2 all the way to AN, then if you raise the sigma to the rth power, you'll get the identity element. Why? Well, you have to think about what does the cycle do to A1, for example? Well, it shifts A1 to A2. Then applying this cycle again, that would shift A2 to A3 and so forth. So one cycle R times, you'll get A1 going back to A1, and similarly for all the other numbers. A2 goes back to A2 after R applications of the function sigma. This applies to any R cycle, whether it's even or odd. And then a useful fact that's a simple consequence is that if sigma of permutation is a product of a disjoint cycles, we've seen in a previous video how to write any permutation as a product of disjoint cycles. And if those cycles have length R1, R2 up to Rj, so sigma is some R1 cycle of length R1, a cycle of length R2, and again, what's important is these cycles are disjoint. In other words, they don't have any numbers in common. Then the order of sigma is the least common multiple of R1, R2 up to Rj. Why is that? Well, when I raise sigma to the R1 power, this cycle becomes the identity element. This cycle may or may not be the identity element. But if I raise sigma to the R2 power, then this cycle will be the identity element. When raised to the R2 power will turn into the identity element, and likewise. And so taking the LCM, that will force sigma, when raised to the LCM of these numbers, all these cycles will turn into the identity element using this idea here. And again, because they're disjoint, there's no interaction. They mess up different numbers, if you will, or mess up or move different numbers. And so we don't have to worry about any interaction between these various cycles. Okay, let's do a concrete example. So let sigma be the element of S9 given by this permutation. So this is the permutation that sends 1 to 3, 2 to 8, and so forth. And then the question is, determine if sigma is an even or odd permutation, and then find the order of sigma. So the solution is to first write sigma as a product of disjoint cycles. The cycle notation is very useful, much more useful than this unwieldy, complicated, matrix notation here. And in a previous video, we've shown how to do that. But when you do that, sigma can be written, for example, as a product of these cycles. How did I get this? Let me quickly review. So you start off with the open parentheses and pick a number that hasn't appeared yet. So we can just pick 1 and then see what happens to 1. So 1 goes to 3. So you write 3 next. Then figure out what does sigma do to 3. Sigma sends 3 to 6. So then you write 6. Then what does sigma do to 6? 6 goes to 1. And so that closes the cycle. So sigma is cycling 1, 3, 6 around. Okay, and then you close this parentheses, and then you open the parentheses, and then pick a number that hasn't been accounted for yet. So for example, I just randomly picked 4, and then do the same analysis, and so on. And then here I've added a number 9 that doesn't get moved around. You can see that 9 just goes to 9, and so it's written as a singleton or a cycle of length 1. Sometimes we just don't even bother writing this. Okay, so now we've written sigma as a product of disjoint cycles, and because this first cycle has length 3, that means, and 3 is odd, that means the associated permutation is even. Remember, that was this unfortunate fact of that. You have to switch from the cycle length, the parity of, or even an oddness of the cycle length, to the parity of the permutation. Okay. So similarly here, this is a 3 cycle, again a cycle length 3, so that's an even permutation. This here is an odd permutation because it's a transposition, a cycle of length 2. 2 is even, so the permutation is odd. Okay, and then 1 is odd, so the associated permutation is even. Here I said you can ignore this because, well, okay. So then we then have to figure out, is sigma even or odd? Well, this cycle here is a product of an even number of transpositions. This is a product of an even number, and then this is a product of an odd number. And so in total, sigma can be written as a product of an even plus an odd transposition, number of transpositions. And so when you add up these things, you get an odd number. If there had been two odds instead of two evens, or even if there had been two evens, but in particular, if there had been two odds, then an odd plus an odd is an even number. But if we just have one odd, then the answer is going to be odd. So sigma is an odd permutation. Then in terms of what is the order of sigma, well, from the cycle type of sigma is 3, 3, 1. What does that mean? Well, we've written sigma as a product of disjoint cycles. Again, here it's very important that the product that you written is disjoint. What does that mean? Well, there's no numbers that occur twice. Okay, like for example, 1, it only occurs in this cycle, it doesn't occur anywhere else. All right, and so this is a cycle of 3, 3, 2, and 1, so that's this notation here. And so the least common multiple of these numbers is 6, and so the order of sigma is 6. Let's compute this in Sage, or check our answer in Sage. So let's construct the symmetric group on 9 letters. That's what I said G equal to. And sigma, I'm just calling it O in Sage here. So we enter the second row of what the original permutation sigma was given by. And then Sage, when we ask Sage, what is O? Well, it gives us this. Note that it doesn't mention 9, because 9 is a singleton, and that's a typical customary thing to do. Okay, and then when I ask for O dot sign, what is the sign, the even and oddness of the permutation? It gives back -1. Now that means that this here, sigma, is a odd permutation. Whereas if it had given +1, then sigma would be a even permutation. Okay, then the order of sigma, or O in this example, is 6, and then if we ask for the cycle type, we get 3, 3, 1.